Welcome back. This video, I want to not dedicate, that's the wrong way to say that. Let me start over again. Molecules have three dimensions. So no matter what it is you look at, whatever the substance, and no matter what phase it's in, solid, liquid, gas, plasma, it doesn't matter. It has three dimensions. You know the fundamentals of an atom. There's a nucleus. The nucleus has protons and neutrons. There's electrons that orbit those nucleus. The nucleus at various energy levels, energy shells. You draw Bohr models, which is not a completely accurate depiction of them, but gets us understanding just the concept of position in space, and then we get it more in depth with electron cloud models, and then we can jump into quantum mechanics, which then changes everything to some degree, and then no degree. It's pretty fascinating, actually. What we're going to do is take a look at with what we understand about bonding. And so particularly we're going to be looking at covalent bonding. So ionic bonding, we're looking at metals, and we're looking at a transfer of electrons. Covalent bonding, we're looking at electrons, particularly, remember, the valence electrons sharing in their valence, their outer orbitals, sharing electrons. So there's a region of space. So if this is an atom and this is an atom, the region of space in between is where we're saying there's a sharing of electrons. Now, and we're going to find out that in another lesson, sometimes that sharing is equal, so to speak, an overall equal sharing, and then sometimes it is an unequal sharing, and that results in certain properties of the molecule, which of course is affected by how it bonds, which is what this lesson is about. So let's go ahead and jump in. Let's take a look at what I have for you. In my class, you already have a copy of this. If not, then it's available from my course website, and you're more than welcome to download that and use it. So we have here what is called, let me change the color of this real quick. So we have here what's called ves-per theory. So ves-per just stands for valence shell electron pair repulsion. And so this makes sense if you think about it. The electrons are in the valence shell. They pair up, and what we've been talking about with Lewis structures, they either pair up in bonding pairs, right, between atoms, or in lone pairs in different regions of space. Either way, a pair is a pair. So we're never going to, and when we're looking at this, we're never looking at a single electron in a region of space by itself. That does occur, but that's a different type of lesson for a different situation. The environment has to change for that to occur. It's talked a little bit in biology class, but if you want, let me know. I can dedicate a video towards talking about what happens when you have just a single electron there. There's various circumstances when that does happen and why it happens. But for this lesson, everything's always in pairs. So if you take a look at this, it's pretty easy to sort of break down. You've got a bunch of columns, you've got a bunch of rows. And so this column here, number of electron domains. So remember, a domain just refers to kind of like a large region of something, or a large amount of something, or an all-encompassing amount of something, everything that's related to that. If you're talking about a domain in biology, it has everything to do with the way we classify organisms and ultimately into this large domain. Here in chemistry, a domain refers to particularly a region of space where electrons are pairing up, okay? And so you don't have to memorize these numbers. After we build these together, after a while, there are certain patterns that show up, and then when you look at it, you just automatically know, wow, there's 2, there's 3, there's 4 domains right there. The next, electron domain geometry. When we're talking about geometry, we're talking about shape, always. Geometry always refers to shape. So we will have terminologies here that refer to shape and form. Bonding domains, that's pretty self-explanatory. How many regions of space have bonds, okay? Non-bonding domains. Non-bonding domains right here would refer to like if you scroll down here, you see where there is a 1 right here. We'll get to this example later, but it basically means where electrons are in lone pairs and not between atoms. That's essentially what that means. Nothing to memorize. After you learn to build these things, you automatically can sort of evaluate the molecules for that. Right here, molecular geometry. It literally means the shape of the molecule. And then, of course, there's some examples right here. Now, you'll notice that over here, you'll notice, I'm going to get rid of all of these things real quick. You'll notice that there is an A and a B that is being used on all these examples. For the purpose of this video, and if you're in my class, I don't use B, I always use X. And the reason for that is because if we go to the next page of this, which you have access to, the next page of this shows X's being used, and then sometimes Y, and we'll get into why. Why? All right, so anyway, go back to what we were doing. Everywhere where there's a B, I'm going to be using the letter X, okay? So what I want you to do is right here in this space, I want you, we're going to call this the molecule type. Now, this is just a very informal way of describing this, okay? This is how it was taught to me. This is what I've read. Sometimes it may just be called a formula type, so to speak, molecule type. It all means the same thing. If we look here at this first example, where you have an A in the middle, there's A, and then there are 2 X's. So we're going to write AX2 on here. So the molecule type, which will sort of help us understand the compound formula. All right, we're going to find that actually does help make a difference with that. The next one down, you can see there's an A, and then there are 3 B's. So I'm going to go AX3. Okay. And then if you look over on the next one down, you'll see that there's an A. There are 2 B's, so I'm going to go AX2. And then we have that non-bonding region right there, that one lone pair. And we're going to denote that with a capital E. Capital E normally means energy. And in here, what it's referring to is the E. It's the way to denote the electrons pairing up in a region of space, in that domain, in that non-bonding domain, right? And electrons carry energy. I don't know if that helps, but use a capital E for this. All right. And so let's take a look. If you look at this example over here, the example that's used is carbon dioxide. Well, we know carbon dioxide is CO2. Well, there's our A, and then there's our X, and notice it follows that pattern right there. It works. And then we've got boron trifluoride. That's boron trifluoride, right? And we can see here that there's our A, and then there's our X. It works. And then right here, you have this ion right here, right? NO2 minus, and you can see that there's the A, there's the X. Now, a formula never has in it the lone pairs in the formula. That's never there. It's implied here that you understand that it's there. Okay, you just have to be aware of that. We use this to help us understand the shape of this, because you can see here that as soon as there was a lone pair, the shape, the basic shape of it is still the same. However, because there's only 2 atoms, we go by a different name, and we'll talk about that here in just a second. All right. So, well, let's talk about it now, since I just already have it on this page. So let's think about this. No, I take that back. Skip that. I'm going to go with my original plan, which is just to go over all this. let's scroll down here, and you can see that we have the domain. There's 4 right here. Tetrahedral. Tetra means 4. All right. We have right here 1A and 4B, so we're going to go AX4. So that's the molecule type. And you can see here we have carbon tetrahydride. So it follows. There's our A, there's our B. And then we have 1A here, and we have 3 B's, so that's AX3, and then there's 1 lone pair. We do that. Nitrogen trihydride, ammonia, right? So that's NH3. There's our A, there's our X. And the lone pairs are just understood to be there. Once you build something enough, you just automatically know there's a lone pair there. And then the next one right here, we have dihydrogen monoxide, water, right? H2O. And so there's an A, and then there's 2 B's, which is AX2, right? And then you've got the 2 lone pairs, so that would be E2. All right. Now, water is one of those where there's the A and then there's the X. But as a rule of thumb, remember hydrogen, as a rule of thumb, tends to show up first in a lot of molecules where we're working with acid and base. All right. And so water, you can get what's called a hydronium atom. All right. And so when you're in an acidic environment, you've got an exchange of ions, the hydroxide and the hydrogen ions back and forth, which changes whether something is more positive or negative, the acidity level of it. And so we follow those rules as far as writing water goes. And OH2, we could do it, but it doesn't sound right. We're just so used to H2O because it follows that pattern that we follow with acids and bases. All right. So let's take a look at this now. Let's look at this. Let's start from the bottom. We're going to work our way back up to the top. So if we look here where we've got tetrahedral, let's go with that first. I've already built it. Here's carbon dihydride, right? And we can see that there's our carbon. So there's the A, and then there's the 1, 2, 3, 4. 4 of those hydrogens. And you can see that no matter which way you turn this molecule, every single angle looks the same. So these bonds are at angles. And so these molecule kits are built to model what we know occurs with molecules, the interaction. The numerous amounts of experimentation and validating of data has occurred to basically let us know that this is what is happening 3-dimensionally. So we build our model kits to represent what our data has already supported. All right, that's what we need to keep in mind. So now scroll down further to the bottom, and you'll notice that there's a whole list here of bond angles for you. And so you can see we can find the tetrahedral conformation, so shape, form, and you can see that the way it's shaped, carbon tetrahydride, tetrahedral, it matches this. And you can see, you have to envision, but there's the center dot right there. And then you can see that no matter where you go, you get that sort of base triangle look. And so you can see here that it's already been calculated that the angles here are 109.5 on average. Now, we've spoken in a previous lesson that matter is in constant motion. It's resonating, it's vibrating, and as a result of that, you have certain types of molecules that have multiple Lewis structure forms. This one does not, but there are those that do. And so that means, if you think about it, these things are constantly moving back and forth. Like right here, I'm trying to keep this still, but those atoms, all the atoms are constantly moving and shifting back and forth. But as the electrons get closer together, they repel back away from each other. And so they're pushing and pulling and repelling on all these sides. And so it averages out to about 109.5 right there. Okay, so that right there. We got tetrahedral form where you've got a central atom and 4 atoms attached. You're going to get that 109.5 degree angle. If we were to take away just one of these right here, right? Then you can see that instead of being a tetrahedral shape, that we have what's called trigonal pyramidal. All right, we have trigonal pyramidal. Trigonal pyramidal, so I'm holding where the lone pairs are. If you look at this ends up taking on a shape that kind of looks like a little squat pyramid. All right, triangle. So there's 1, 2, 3 angles. So in the absence of this one atom right here, this lone pair right here, it keeps these angles down this way, but there's not an atom here that's taking up more space and pushing these a little further down. So what happens is the angles change just ever so slightly, and the angle that you get is about 107 degrees. So we go from 109.5 degrees to 107 degrees. It changes just a little bit. It decreases just a little bit. All right. And the reason for that is because these lone pairs, the way that they're pushing, these electrons right here are pushing, they change and adjust these angles where they're not being pushed out quite as much. Pretty much close. It averages out about 107. All right. So that's trigonal pyramidal. Come down here to where we have our water molecule. And you can see what happens is we went from one atom being replaced to now 2 atoms being replaced with lone pairs. All right, and that right there is putting stress in such a way from multiple angles that it bends these 2 hydrogen atoms, whatever's here, bends them down a little bit further to around 105 degrees. And we get what is called a bent form, all right? And so that's the geometry. Now, all 3 of these, all right? All 3 of these right here, all 3 of these are a tetrahedral domain geometry because there are 4 regions of space around the central atom. All right, 4 regions of space. It doesn't matter. Bonding pairs, non-bonding pairs, right? Non-bonding pairs, non-bonding domains, bonding domains. There's 4. So they're all tetrahedral as far as that goes. But their molecular geometry changes. You got tetrahedral, this is your trigonal pyramidal, and then you got bent. All right. So because the angles change a little bit, we use a little bit of some geometry terminology to identify that particular form, all right? And then there's a couple of others, but there's one I want to really bring to your attention, right? And so, well, first before I forget, so down here we talked about bent for water, but then notice that we have something right here that also says bent. Before I talk about this one, let me talk about this one. All right, and I realize there's a lot on the screen, but right now, let's talk about that right there. Trigonal planar. So trigonal, try like 3 angles, right? So there's an angle here, there's an angle here, and there's an angle here. Now green is normally chlorine. This beige color right here, it represents the boron atom. But I'm just using green because this right here, this example, boron trifluoride, chlorine and fluorine being in group 17, being halogens, I decided I can just substitute it. It's just a color. If I could paint this a different color to represent the fluorine, it does. It represents that. Now, what you have to envision, though, is that remember that right here, each fluorine has 7 valence electrons already. So that means that around this fluorine right here, there are 1, 2, 3 lone pairs. That's 2, 4, 6, and it's bringing in that one right here that's being shared right here with the boron, all right? So you have to envision that there are 3 lone pairs here, there are 3 lone pairs here, and there are 3 lone pairs here. But all of those interactions are in such a way that it causes the molecule to sit on a singular plane. So if you look, you can see it's sitting on a very singular plane, which is why it's called a planar form. So trigonal planar, 3 angles on one single plane. Now, if all of a sudden this atom right here were to go away, then there's now nothing else left bonding right here. So what that means is all of a sudden now we've got a pair of electrons here, a lone pair of electrons. Now if you look at this, and you look at this, the 2 atoms are shaped pretty much the same, which is why we call this bent as well as calling this bent. All right. The only difference is this particular atom, the central atom, it cannot have it cannot hold a second lone pair, but because of the way that it interacts with the other atoms that are here, it still forms a bent sort of shape, and so we say bent. All right. And that's really the beginnings of VSEPR theory. So whenever you draw your molecules, you figure out what's your domain. That'll be then, of course, that'll be the shape, right? Et cetera, et cetera, et cetera. And then you follow this, you just move yourself over to where it talks about the geometry, and the geometry name is there. You just follow that. And then you also have over here, you've got what are called space-filling models. All right, these are space-filling models where it kind of shows the bonding interactions and how it's affecting the shape of the molecule. We will talk about that some more, but you'll see that the geometric terminologies are there and the same basic shapes are there. It ignores the lone pairs. It pretends you know that they're there or not there. You're just looking at what's the overall sort of 3D space filling that's going on. And then down here, this deals with polarity. That'll be another lesson that I will have with you where I will dedicate solely to talking about molecular polarity. So I hope this helped. Hope you enjoyed it. Thanks for coming back, and then it's always fun learning with you. So go get some coffee and move on to the next lesson. Good studying. Talk to you soon. Bye.